Alright, we are finally at the end of this course, just the last mile, the last section about this long journey through the mathematical foundations of machine learning. And this section is the hardest one, the most difficult, not for us that we have to study it, but for the model. In fact, through the knowledge we acquired, we gained through the previous courses, we are now able to deal and build novel models, the best we can find and think about it. But a model is nothing if it does not work in production. In industry, what matters is a model that works in production, not the type of fancy model you choose or how many dollars you have spent on the Google Cloud to train that model. What counts is if it works, and if it works in the real world. So in this section, talking about model validation, we will I will introduce you some techniques to make sure, or at least try to make sure that the model will do well in the real world. So, as I always present it to you, this is how we see the phenomenon that we want to study, or on which we want to develop the project. And what we can observe is this, the observed sample, which is some information gained from the sample space, the whole population, through a sampling scheme. And with the observed sample, we want to build a statistical inference tool, a statistical model, a machine learning model in particular, to describe the entire population, even what we are not yet able to see, but with some regions of the sample space that are not inside the observed sample could be approached in production. So our goal is, thanks to this observed sample, to generalize the behavior of the statistical model, the good performance we gained on the observed model through the entire sample space. But there's a problem. Machine learning models are lazy because, after all, we train them to be so. We are actually minimizing the error. And the models try to find the best way, the laziness way to discover that minimum of the risk function, the empirical risk function. So we have to try to validate the predictive capabilities of the model. In particular, we can divide the whole dataset, the observed sample, into two or three subsets. This training set will be the set of data, usually a lot of data, that will be fed into the model, so it can learn the best parameters that minimize the empirical risk function on the training set. But there are also at least one other set, the test set. And the test set is some sort of data that is sampled from the observed space that is not used to train the model, because these two sets contain different data. And after we train the data, we get the model is finally fine-tuned. We say, yes, this is my final model. These are the performance on the training set. But the model could also reach the best performance in the world on the training set. It could memorize every every data point in the training set. But this approach would not work with either other data. That's why we bring also a test set. and we test the model, the trained model, on the test set. If the model does not perform very well, and in particular if the performance between the predictive capabilities on the training set on the test set largely diverge, this means that we have a problem. If the model does not work very well in the test set, imagine in production, where we have no control on the data we acquire and that we feed as input to the model. Finally, we can select another subset of data, the validation set. So remember, the principle is that in the training set, the training set is used to train the model. Okay. The test set is used to test the predictive capabilities of the model once it is fine-tuned, once it is packaged. The validation set is used during the training phase, but to decide to choose the best hyperparameters. So, when choosing we have seen in the previous section that we have first to choose the hyperparameters, then we train the model, and the model, through the optimization problem, finds the best parameters. So the training set is used here, which contains a large part of the data in the observed sample, is used to determine the parameters. But how can I choose the hyperparameters? Well, I select some parameters, and with this in mind, I train the model. But then I need to test the performance of that parameters on a validation set. This allows me to, the training set allows me to choose the best parameters, the validation set allows me to test the hyperparameters, and then I have finally the test set that allows me to test the whole model. But there are more advanced techniques. For example, the Kfold cross-validation. In the previous approach, we took the observed sample, select some percentage, and randomly sampled the data points in the observed sample, in the training set, the validation, and the test set. Now we are doing something more complicated. Imagine that these both are our data set. And imagine that we are not considering the validation set. So we have only test set or test data and training data. Here we select a k number, a Kfold, which will be also the number of iteration that will be done in this advanced technique. We randomly sample the data, and then we choose the first percentage will be our test set in the first iteration. So with this training data, I train the model, and then I test its performance on the test data. All right, that's so. In a spreadsheet, I saved iteration 1. Test data was that. The performance of the model on the test data are X. Iteration 2. This is the new test data, and the other balls that are not highlighted here. So this set of balls that previously were part of the test data are now part of the training data, and also this one. So again, I take the raw model, forgetting about the previous iteration, and I train the model again with other data now. Again, the trained model is tested on what? On this test set now. I go again on the spreadsheet, I write iteration 2, test set depth, this one. This was the performance on this test set. And I repeat this k times. Why? Because I have k folds here. I divided in k chunks of data, and for each iteration, one of the chunk was my test set. Why I use this technique? Because I can measure the variance between that the model produces when changing the training data. Because here the data set is always the same, but since I trained the model always and at each iteration with a different training set, and I also test the trained model on a different test set, I can measure how the performance change if I train the model on different data. So this determines the stability of the model. So in generally, the performance that is shown is when using Kfold cross-validation is usually the mean of the performances on the k iterations or the best one. But looking at the mean, if the mean has a large variance, this means that the model is unstable. And if it is unstable in our observed sample, imagine on the whole population. It will be a mess. The model will not perform good at all. It would perform very poorly. And here you can see another view of the same with this picture. You can see the Kfold cross-validation with the folds as rectangles. So here I use a 5-fold cross-validation. I divide the training data into 5 folds, and each of the fold through the split, the iteration, will be my validation set. Now, because the test set is a different part of all my data set. So the fold 1, 2, 3, 4, and 5 here are validation sets. And then if I say that the model seems stable using this approach, then I can test again with this test data. But since the process is from population to observed sample to sampling scheme and observed sample to population through a machine learning model, some problems can occur in the two phases. Let's analyze a little bit about these sampling problems. And here I have selected 4 examples, 4 common problems during this sample that are related to our sampling scheme. The dataset partitioning errors, the covariate shift, the probability shift, and the selection bias. Let's start with the first one, the dataset partitioning error. It means that we are sampling, we are building our training and test set in a wrong way. For example, in this picture, we have the true function, the phenomenon, is this line. But we made a mistake. We took as training samples, the data points are the blue dots and the black cross. here. And I made a mistake because I divided the two sets, the training and the test set, through basically an x value. I say the data points that have x value beyond a certain value are I put them in the training set, and in the test set, and the values below that x value will be put into the training set. So I fit a model, and the model, for example, a linear regression model, and the model seems to perform very good in the training set. But I made a data partitioning error because I did not consider these points. The model didn't explore this part of the domain region when trained. So it can do whatever it wants here, because it is never been trained with x values like this one. So to avoid the data partitioning error, for example in this case, a better approach would be to choose randomly, with a certain probability, if a certain data point should be put in the training set or in the test set. So here the points would be selected randomly, and maybe a test sample would be here, but also the training samples, some of the training samples will lie with these x values. So I can build a better machine learning model. Second sampling problem would be covariate shift. It means that here I have labeled and unlabeled. For us, it means that labeled is what I see on when I get observed the data, the phenomenon. I get the data and I train a model in it. Then I go on production and I get some, let's say, unlabeled data. Well, we talk about covariate shift. If the domain in which the data points lie vary between the training phase and the production phase. For example, here I used a simple model, again, linear regression. But considering only the black triangles here, which are the data points that were inside my training set, I developed this machine learning model, this line. Then I go on production, and these are the points, the red squares here. So the domain of our covariates shifted from training to production, maybe because to develop the data was very old, and the world in the meantime, when I collected the data, trained the model and so on, some years could have been passed between me collecting the data and me sending in production the model. For example, I trained the model. I wanted to train a model using informations from people, for example, the age, and I want to predict something. In the training dataset, I have a lot of young people here. So I train, this is my training set. I develop the model. The optimization is done thinking about this data set, and I develop a score. Then when I go in the testing phase, or even worse, in the production phase, I get this dataset. A lot of old people here. And I want to predict using the score using the same model. Well, the model will predict very poorly because it is not trained on old people, it's trained on young people. So the testing score or even the production score, the production behavior of the model would be bad than expected, than with respect to what I have seen in the training phase. That's a huge problem. And the third sampling problem is even worse. But we can deal with it, but not as we can do, for example, with the covariate shift. We can, with probability shift, we cannot do a lot. And this means that in probability, while in the covariate shift, the domain of the phenomenon changes, in the probability shift, the phenomenon itself changes. Its probability distribution changes. So, for example, let's say we want to predict the probability distribution of the heart temperature in a year. Year by year, the probability distribution changed quite a lot. You know that as pointed by this article, the global annual average temperature is increasing quite a lot. The probability, the phenomenon is shifting. So if I developed, for example, a model in 2005, the prediction will be very poor if I took 11 years to put it on production, because this is now the probability distribution. So it's a huge problem. It can destroy the work I've done through the training of a model, but I cannot deal with it, unfortunately. For example, another example of probability shift: the deaths before and during the COVID-19 pandemic in Italy, for example, because I'm Italian and this is the data I could find. So these are the annual deaths. Without considering the red one, you can see that the deaths during the year follow some sort of pattern. But with COVID-19, this pattern breaks. Is totally different. The phenomenon changed because it was a pandemic. We are dealing with a new virus that made a lot of deaths. So if we are, for example, here in the years between 2015 and 2019, we could have developed a linear regression model to predict the deaths during the year. But we cannot use that model in 2020 because we have the COVID. The coronavirus breaks our model. It makes no sense to still use it. And the fourth sampling problem is the selection bias. And a particular type of selection bias is the survivorship bias. And I bring to you two examples of survivorship bias. The first one is about planes. As you can see in this picture, we have planes that are coming home from battle, having bullet holes everywhere, as you can see, but not in the engine and the cockpit. you see here no bullets at all. So an engineer could say, well, all right, we can put armor everywhere, but not in the engine and the cockpit, and the plane would be a lot more robust. But is forgetting something, that here we are recording the data because these planes were able to come home. The ones who did not come home were in fact because they get hit in the cockpit or in the engines. This is a survivorship bias. We are looking at an observed sample that is selected. Another example would be the investment funds. If we, for example, we want to compute, we want to take an index, all right, which in which several investment funds trade. And for example, we want to, let's look at 2015. We want in 2016, we want to see which is the mean return that that index, for example, the Euro Stock index, did. If we are looking with the data in the late 2015 or in 2016, we see that the return is about 18%. But here we have another bar that says 15. So who's right? Well, we are looking at the end of 2015, so we are taking care only about the index that were able to survive through the year. We are not considering all the stocks or the the investment funds that did fail, that they went broke. That's why, considering every investment fund, for example, that was trading in 2015, we get a lower mean return, because some company did zero or maybe lost all its capital. And then we can approach the other part of the problem, from the observed sample to the population, through our developed machine learning model. And again, I want to bring you 4 examples of training problems. But to deal with them, I want to show you another property of training a model, and this is the loss curve. We've seen that the optimization problem is solved through an iterative training, an iterative process, for example, the gradient descent we've seen. And each iteration here through the whole dataset is called epoch. And here the law is called loss, but again is the empirical risk function. Takes values that became smaller and smaller because we are optimizing, we are reducing the error, the risk function values. And this is the loss curve, the risk function values through the epochs. And we can see a loss function for the training set and also for the validation set, because at the end of each epoch we can take that model, the trained model, and test it on the validation set, for example. And record what are the performance in that epoch in the validation set. Then we can train again another epoch. We take the model as it is and we test it on, we measure the performance on the validation set, for example. We record that data and this becomes another loss curve, but that refers to the validation set, for example. So what are the training problems? The wrong validation technique that we are using to optimizing and selecting the model, the overfitting, the development of a bias model, and finally, the adversarial attacks. Let's start with the first one. And we can see here a particular data set, here a time series data, in which we have this feature window that is our data, and we want to predict our features, and we want to predict this orange values. So we are doing forecasting, but we cannot apply here training validation and test split technique, or even cross-validation. Why? Because in the standard training validation test split, we are considering the sample as to be IID, independent, and each sample is independent and identically distributed. This is not true in a time series, otherwise it would not be a time series. The data is dependent one between the other. We are in a time series, so this is it's wrong to apply in a time series the standard training validation and test set split, or even the standard cross validation. A better approach, the right approach, would be to use an validation, a more specific validation technique. For example, the time series nested cross validation, in which is still a cross validation technique, but not a Kfold validation, because in here the faults are chosen not randomly, but in a consequently a way. Here we have that the blue, in the blue color we have the train set, in the yellow color we have the validation set, and the red one we have the test set. As you can see, the training set, here we do not shuffle the data as in the cross-validation, in the Kfold cross-validation presented here. We do not shuffle the data. The data keeps the order, the time order, and we use the training data also in order. This is one of the possible right validation techniques that can be used in time series. Let's talk about the second training problem, which is overfitting. What does it mean, overfitting? Well, here by prediction error we mean the risk function value, and here by model complexity we are considering the epochs. So through the epochs, the training loss curve will reach lower and lower values of errors. Of course, we are optimizing the model. We are choosing the best parameters that allow us to reduce the prediction error. But that's a problem, because if we also consider the test data or the validation data, then this loss curve keeps getting lower and lower until a certain point, the optimal point. And if we continue, then the test data the prediction error on the test data increases. Surprisingly, no, because we are optimizing the training data, the model on the training data, but we've seen that the model is lazy. And for example, when you want to pass an exam, the easy way to learn those concepts would be to remember it, to memorize that concept, not to understand the general concept. The faster way is to memorize. And I could say the optimal way. That's what a machine learning model does. It learns, and it learns until a certain point to get a lower and a lower prediction error. It starts to memorize the training data. And this is a problem because the data that the data points that lie inside the training data are not inside the test data or the validation data. This means that after the optimal point, the model is discarding the general understanding, we could say, about the phenomenon, and only memorizes the training data. That's why it does worse on the test data. This process of memorization of the data points, the data, is called overfitting. It means that the model is adapting too much on the training set and is losing its generalization power. And imagine if the model is overfitting on the test data, it could only get worse on production. So the ideal point here is to choose the model in the epoch in which the two loss curve start to diverge, and this optimal point can be reached through an early stopping. We stop the training when we see the two loss curve diverge. Third training problem, and this is the development of a bias model. The model learns a general concept and usually it is able to extrapolate some, we can talk about knowledge, but it's only the correlations between the data that even humans cannot maybe get through a first looking of the data. And this is, for example, what happened in this paper here, where these researchers were able to scientifically demonstrate that the newspaper are biased because a model trained on the newspaper data is able to correlate a woman to a computer programmer and a woman to an homemaker. This means that the model just amplifies the bias that lies inside the data. And this could be a problem. For example, it happened quite a few years ago that someone, white people, trained a model to recognize faces. What type of images did they put on its training set? The most familiar ones of white people. But on production, that model was looking at white or black people and could not recognize the black people faces because he has never been trained on that. So the model just amplified the bias that the people who get the training set let inside it. And the last training problem that, as an example, I show to you are the adversarial attacks. Because usually the training set is not a lot big, and we are not able to explore the whole behavior of the model. We explore the behavior of the model through the dataset we have on our hands. And these adversarial attacks are a strange phenomenon that happens in the training models. For example, here we have our trained model that is able to classify images. And taking a look to this image, the model predicts that is a panda with about 58% of confidence. But if we add some random noise to this picture, it just blurs a little bit the picture. The model will predict with an almost certainty that in this picture there's a gibbon. This is a huge problem and is still studied, and researchers are trying to demonstrate that this noise, this chosen noise, discovers a new domain on the machine learning model that has not been explored through the training set, and because of that, the results can be incredible and completely unexpected. Also, adversarial attacks can even be common to different models. For example, if we train two different models on tabular data and we find an adversarial attack, an adversarial example for one of the model, it could be also an adversarial attack for the other model. So I talked to you about sampling problems and training problems, but remember that we are trying to deal with these problems using the test set, which is still part of our observed sample. So what we care is not even here, not even in the test set, but in the data we will collect on production. So the test set is just an approximation of what we can find outside in the real world. And all the problems we have discovered since now can affect the test set. Imagine in production. That's why I say that the math is beautiful. We have done 5 courses on math, and with this we can develop the most astonishing machine learning models we can even think about it. But if that model does not work on production, not on the training, validation, or test set, what an industry cares is the behavior of the model in production. And if it does not work, the time, the effort, it means nothing. Another problem with machine learning models, the interpolation versus the extrapolation. The machine learning models are very good at interpolating the data, but they are usually very bad at extrapolation. In extrapolation, it means that we took a a point that is very far from our training data. In the interpolation instead, we took a point that is close to the domain that we used to train the model. So, for example, here, that's what we see during training. We want to develop a classifier, a model that classifies these points. So the features are, we have two features, x1 and x2, and a label 0, 1, 2. The model has to take in input the x1 and x2 and predict if that point behaves in the 0 cluster, the 1 cluster, on the second cluster. This is what we see in production. But something could go wrong. This is what we see during training, but something could go wrong in production, because this is how the model behaves. So in the shadow regions, the model is not a lot certain about the predictions. But in the red, green, and blue regions, the model is very sure about its prediction. If we took a point down here, it will predict with a high confidence that this will be part of the cluster 0. But is it right? I mean, why a point here should be part of this cluster, this cloud of points? Why? It's a lot far. The behavior far from what we have seen in our training set is not explored. And this could be even worse, because the model does this, whatever xy and x2 are. Does it have a sense? I would never trust a model that behaves like this in production. It could be very dangerous, because I never explored those regions, and the model instead keeps predicting the cluster with a high probability. Is not unsure here, for example. And this happens, of course, in different ways, but with almost every machine learning model. For example, here or here. For example, here we are using a decision tree. That's the same, a random forest, the same problem. How can we assess this problem? But, well, a possible solution could be to limit the domain of the model. We can use a lot of techniques, but we can say that, all right, model, if you receive on production a data point that lies inside this region, then I let you predict the cluster. If a point lies outside the region I told you, do not predict anything. Let me deal with that. And I want to show you another example of the problems that could happen when we have to deal when training a machine learning model. And I want to tell you about the story about Tatiana Sennikilova, about the her pigeon avoidance system. You can find their story. Let me show you here. Yeah, on how to use deep learning to show pigeons from the balcony. Tatiana Sennikova in Towards Data Science. So, what's the problem that Tatiana want to solve. Well, pigeons on the balcony. What solution did she develop? Well, she wanted to detect if the pigeon sits on the balcony, and then with a system to show him. So here we focus on the detection part. We need to develop a machine learning model, in particular a convolutional neural network. And Tatiana trained this machine learning model to classify from the webcam input if the pigeon was on the balcony or not. The results seem quite good. So we have our machine learning model that with this picture says alert pigeon on the balcony, activate the show system. But one day the pigeons began to build a nest in the tree in front of the balcony. So they began to carry some twigs, and the model started to fail to classify them. The model could not recognize a pigeon with a twig. So with this picture, the model would say no pigeons on the balcony. What Tatiana did? Well, it took these pictures and retrained the model with them. Tatiana added those pictures on the dataset and retrained the model. But in this way, the model focused too much on the sticks compared to the pigeon morphology. And this can be seen by this picture. Tatiana was carrying some sticks, and the model said the alert pigeon on the balcony, activate the show system. The model get biased through the sticks and could not generalize about the morphology of a pigeon. In here you can see the system, a pigeon on the balcony, the system detects, and here is the show system that Tatiana developed. So machine learning can have strange behaviors when on production, because during the validation phase, or the test phase, or even in the training phase, not all the sample space can be explored. Of course, we have only a portion of the population of the sample space, our observed sample. And outside the observed sample, the model can behave how it wants. So the model in those regions could have strange behaviors, and you have to be very careful to deal with it. For example, reducing the regions in which the model can predict something, as we've seen in the previous slides. So this is the end. Brick after brick, we have built a strong foundation, the mathematical foundation of machine learning. Now it's time for you to show to the world what you can do with this knowledge. See you next time. Bye.